It's all Greek to me, huh? I'd like to thank Ming for the invitation to come talk about the latest and greatest under the hood for the most recent WIP recertification compliance application. I thought I did. Can you hear me okay in the back now? Okay. So here's an outline of what I'm going to go over. Just so that we're all on the same page starting out, I'll talk a little bit about WIP. It's been in the news lately. You may have heard of it. Probably more than you want to have. Specifically talk about the release mechanisms we consider in PA and the compliance metric that we use to demonstrate regulatory compliance. Then we'll get into the meat of what's in the 2014 WIP CRA. There are a number of plan changes proposed by the Department of Energy that are in there, standard updates that we do, and there are parameter implementation refinements also included. And because there's so many changes included in this performance assessment, we've taken a little bit different approach than we have in the past. So we can step through the analysis easier, and we can walk the regulator through that analysis easier instead of just throwing a big boulder over the fence to them and ask them to catch it. We can sort of prepare them for what's coming. And then talk about the summary of what we found at the end. So just so we're all starting on the same, I'm sure you guys have seen this before. WIP's a permanent disposal facility for transuranic waste. It's located in southeastern New Mexico. It's operated by the US DOE. Long-term performance is regulated by the Environmental Protection Agency. We interact with them extensively. Waste is placed in a salt formation deep underground. And long-term performance is demonstrated by PA that's conducted by the group I'm in Carlsbad, New Mexico. I think that's a laser P&RA. So currently, here's the configuration as it stands now. So there are 10 waste panels in the south, 4 eastern panels, 4 western panels. There'll be 2 future panels in the center drifts area. Then there's an operations region here where there's no waste, and an experimental region here where there's no waste, and 4 shafts. If you've been following the news, so these panels are full, these 2 panels are full, and that panel was just beginning to be filled when the drum breached, and it's right in room 7 of panel 7. So each panel had 7 rooms. They're roughly the size of a football field. And so where the breach happened was right as this panel was being filled, right in that corner, roughly. So WIP is an operating facility, and we have regulations that we have to meet and demonstrate that it complies with. So there was talk some yesterday about the time scale you could do a PA toward. Maybe it's better to do a shorter time scale and then sort of leapfrog that forward. We don't have that luxury with WIP. So right in the regulation, it tells us how far out we have to demonstrate compliance for. So I'll just read what this says. The WIP must be designed to provide reasonable expectation that cumulative releases of radionuclides to the accessible environment for 10,000 years, so there's our time scale, after disposal from all significant processes and events shall be less than specified release limits. So there's not really any wiggle room for us in trying to sort of leapfrog a shorter time scale forward. It has to be for that whole 10,000 years after closure. So there's some language in there that guides what we do in PA for WIP. So reasonable expectation, regulations acknowledge that there are substantial uncertainties, and we're over a long time scale, so the regulator doesn't expect us to give them a deterministic answer at the end. This is exactly what's going to happen. There's a lot of uncertainty that we capture. 10,000 years, I've sort of hammered on this already. We have to predict behavior for the full regulatory time period after closure. Significant processes and events. PA must include all of these, including the possibility of human intrusion. That's done through a FEP screening, where things are looked at and included or discarded in the performance assessment. And some of the things that are included can also come directly from the regulator. They may say, this is something we're concerned about that's going to be included. So what's going to be in there? Here's the release pathways. I'll say more about the meat of these in the next few slides. So we look at performance for WIP for undisturbed and a disturbed condition. And those are both represented on this schematic. So undisturbed would be, you have the waste sitting down here, and over 10,000 years, That waste gets wet, kicks off gas generation, that waste area gets pressurized more and more, and it may migrate, transport radionuclides outside the panel closures over time, slowly up the sealed shaft. As that brine moves, it may interact with these lateral flow pathways to the anhydrites. The calabres are a zone of fractured dolomite above the whip that is the most transmissive zone laterally. So over time, that brine may move up, move out, move up higher, move out. Somebody's already wanting to make changes to my sentence. Maybe something's wrong on this slide. I don't think so. So over 10,000 years for the undisturbed case, we tally cumulative flows outside what's called the land withdrawal boundary. And you'll see a picture of that in a slide coming up, but there's basically a box put around WIP, and we track everything that moves outside of that box laterally. So that's for the undisturbed scenario. For disturbed, there's a lot of oil and gas resources in that area, and companies are sitting down boreholes to extract those resources all the time. So suppose in the future, not knowing anybody any better, somebody goes out there and sinks a borehole down through WIP, what happens? So that's the disturbed scenarios that we look at. Somebody goes out there and drills, intersects the repository, either they stop there and that material gets pulled up, or they drill further, interact a region of pressurized brine below the repository. That brine comes up, floods the waste. That can impact pressures and brine saturations and all those sorts of things in the waste, and that can impact releases later. So those are the release pathways we look at. I'll say more specifically about what these mechanisms are, but we look at undisturbed and disturbed performance. So in performance assessment, and we'll see this in the results that I'm going to show towards the end, for WIP at least, direct release mechanisms really dominate our compliance curves. And those direct release mechanisms are cuttings. So the waste is here, a company comes in the future and sinks a borehole down through the waste, and that material that gets pulled up directly, that's a cuttings release. Cavings releases, as they're boring out this hole, they have fluid that's circulating in the borehole, and that fluid erodes waste additionally and pulls more waste up in addition to what was brought up by cuttings. Spallings, if that waste has interacted with brine and you've had gas generation, build up pressure, when they puncture the waste, you can have a pressure release that will take waste and push it up and out the borehole. And then direct brine releases are just releases of brine that have waste material dissolved in it. So those are the types of release mechanisms that we look at in WIP PA. And we'll see coming up soon, cuttings and cavings dominate and are followed by direct brine releases. Here's the picture of WIP I was talking about a second ago. So as I said, there's a lot of oil and gas resources in that area, and you can see they're checkerboarding that whole region trying to get at them. So you have a nice little clean box here where WIP is surrounded by lots of boreholes. This box here is the land withdrawal boundary, so we tally what cumulatively flows outside of that box. Then our long-term releases are radionuclide transport through the groundwater. So either that brine, when somebody comes in the future and intrudes the repository, it can come and mix through the waste and come out and through the calabra and cross this boundary, or it can come up the shaft through the calabra and cross that boundary. We track all of that. And we're also, by regulation, specified how we illustrate compliance. We use what's called CCDFs, complementary cumulative distribution functions. And we have our regulatory release limits that are prescribed to us by the EPA. And that's what these curves are here. So this corner is less than 1 chance in 10 of exceeding 1 EPA unit, less than 1 chance in 1,000 of exceeding 10 EP units here. So we look at each release component we have, spallings, this one, direct brine releases, cuttings and cavings. We can look at those and pick out which release mechanisms dominate. It's almost always cuttings and cavings, which is this curve, and direct brine releases. Those two things together give us almost all the releases that we see when we run a PA for WIP. And the current regulatory baseline was that established in 2009. That's what this, hopefully you can read that in the back. It may be kind of small. The PABC 2009 is performance assessment baseline calculation in 2009. That's the current blessed PA by the EPA for WIP. So that's the one that we currently compare back to see what the changes we've included since due to regulatory performance. So these are all mean curves, and they're means of 300 individual CCDFs. Here's an example for direct brine releases. So I said we have uncertainty that's captured in many of these parameters. We run enough realizations to capture the spread of responses over that uncertainty range. This for direct brine releases, you see some where you don't have that many releases, some where you have a little higher out here. These are useful in that they can provide insight to us on what sort of parameter combinations give you a higher release. So once we have our individual components in the horsetail plot, that's what I'll call this from now on, because that's just what we call those. We compare total releases to the regulatory compliance curve. So this black curve is our current blessed performance assessment result that's accepted by the EPA. So that's the one we'll be comparing against later. And so before we get into the approach and results for the 2014 CRA, here's a little schematic to keep in mind for the overall flow that WIP PA does. So we start out with a screening of features, events, and processes. What's important to include, what can we discard, what things have been mandated to us by the regulator has to be in there. Once we have our hands around those, we use those to develop scenarios using our screened in FEPS. And because we're going out to 10,000 years and we have resources in that area, we don't know exactly when or if someone's going to puncture that repository trying to get at oil. So we model that uncertainty. Aleatory uncertainty is captured here in the scenario development. Once you have our scenarios figured out, and we build up our overall repository conceptual model, that conceptual model feeds into sets of partial differential equations, mathematical process models that have parameters in them that have significant uncertainty associated with them. So that's where we pick up our epistemic uncertainty. We take those PDE models, numerically implement them, turn the crank, and get release probabilities with quantified uncertainty. So we go through this process not only when WIP is recertifying, but also when the department has a change they want to make to the repository. They have to go forward to the EPA and demonstrate to them what sort of changes that those modifications will make to compliance. So this process we step through every time we run a PA to show to either the DOE or the EPA when we're demonstrating compliance. So our regulations require that WIP must be certified every 5 years following the first waste shipment of 1999. There's not a lot of waste going into WIP right now, but there's been a little bit coming out. But yeah. I probably shouldn't joke about that. So as I mentioned, the current regulatory baseline is that established by the PABC 2009. Performance assessment baseline calculation. The one that we just submitted to the EPA in March of 2014 demonstrates continued compliance with the regulatory standards for WIP as it stands now.
That was before the accident.
Right, before that. That's what I was just going to say. So there's a data cutoff after which we don't include new information in the performance assessment. So yeah, so the next one that's going to be in there. But for this one, there's nothing about the release event. It was already written up and almost ready to be submitted when that happened. So now we'll change gears a bit. Talk about there are two plan changes proposed by the Department of Energy that are included in this CRA. And we'll talk a bit about both of those. The first one is a change to the panel closure design that was originally accepted in WIP. That's been revised, redesigned, approved by the EPA through a federal rulemaking process. Essentially, the law had to be changed to allow this panel closure in the repository. So we'll talk about that. And then additional excavated volume in the north end to carry out salt disposal investigation experiments. So we'll take a little detour here and talk a bit about both of these. So from the top down, here's how WIP looks now. So you see here's our 10 waste panels, here's the operations area, here's the experimental area, and the shafts located in the northern end. And it may be hard to see in the back, but there's little black symbols here on the outlet and the inlet of each panel. Those are panel closures. There's a set of panel closures here, a set here, and a set here. And WIP panel closures have been included in PA since the original 1996 compliance recertification. And it's important to note that they're not included in PA because they have a significant impact on long-term performance. They're just a feature of the repository that's there, so we have to model it. They're primarily there to protect workers during the operational phase of the facility. So that's important. So in 2011, I believe it was, the DOE submitted a plan change request. There's some fancy language. So there's a level of formality with these requests that the DOE makes. The plan change request is fairly formal and has to have a big analysis with it. The EPA is very formal in how they respond to it. And that's the process that was underwent to request a formal change to the approved panel closure design. The panel closure design was changed to a run-of-mine panel closure system, which I'll call ROMP PCS, probably from here on out, with approval via a federal rulemaking process. That was a very arduous task for the regulator to undertake. They wanted to know that this panel closure design is not going to negatively impact performance before they sort of step into this big cog they had to do to change the law. So we spent a lot of time interacting with the regulator to develop the ROM PCS parameters and temporal timings. It was roughly 1.5 years where we negotiated these parameters with the EPA. The new panel closure is designed as 100 feet of run-of-mine salt. Calculations and data analyses were performed to determine the parameters important to that model and how they change over time. And numerous technical exchanges were held with the EPA to discuss and refine the panel closure representation in PA. It was important to us and it was important to them to reach a consensus on what we thought these parameters should be and how they change over time before they threw themselves into that federal rulemaking process. I think that's a rough deal for them, and we wanted to make sure they would be okay going through that.
Explain what you mean by 100 feet run-of-mine salt.
Oh, okay, so WIP, I should have said when the picture was up. So WIP's in a bedded salt formation. So just as they mine the panels out, what they pull out is just called run-of-mine salt. So it's just loose chunks of salt, rock salt.
Seals used to be concrete, right?
Yeah, yep, the option D was a big concrete monolith.
Use salt instead.
Mm-hmm. Yeah, just because they have it there and creep closures can become and compact it. The temporal evolution of these new panel closures was something that took a good bit of negotiation with the regulator on until they felt comfortable with it and we felt comfortable with it. Its model is having short-term and long-term characteristics with properties based on 3 time periods. So for 0 to 100 years, the in-place run-of-mine salt, you have creep closure hitting it on the top and bottom, so you have some reconsolidation, but the back stress on the surrounding salt rock's not high enough yet to reconsolidate the damaged rock zone. There's no impact on the surrounding salt rock. From 100 to 200 years, creep continues. That panel closure continues to reconsolidate with no impact on the surrounding rock. And from 200 years to the final time of 10,000 years, that panel closure is fully healed. It has exerted enough back stress on the surrounding rock zone, but the disturbed rock zone is also healed. And one note I have here to make sure to mention, it was important to keep a good relationship with the regulator during this process and to just talk through step by step what we want to do and to get their input on it. So they had a big hand also in determining these time scales, just until we all had a consensus built and we were ready to push the switch on PA and run it. So that's all I'm going to say about the new panel closure design. The second plan change request, this was a plan change notice, so that implies a less degree of formality by the department to the EPA. So a plan change request is essentially the DOE going to EPA and asking for permission to do something. A plan change notice is they're just notifying the agency, this is the change we're going to make. So the new excavation for salt disposal investigation was a plan change notice because the change occurs in the north end here, not down here where the waste is. So what the department proposes to do here, and has done, is to mine out some additional drifts in the north end and to basically have an underground salt lab in the north end of WIP. So they could do experiments there for heat generating material and see how that behaves in salt. And the impacts that has on the temporal and physical characteristics of the surrounding salt rock. So there were 60,000 roughly cubic meters of additional excavated volume that was included in the north end of the repository. And so even though that change doesn't occur where there's any waste, it can still impact what's happening down here. So that's why we had to do an impact assessment to show the EPA this really isn't going to impact anything. We've looked at all the things that they could do. So an increased experimental volume potentially reduces pressure in the experimental region. That pressure reduction over time may be seen in the waste area. A waste area pressure reduction may allow more brine to flow into those waste panels. That can kick off increased gas generation. You may have a little higher pressure. And two of the release mechanisms depend directly on pressure and brine saturation. So spallings is directly dependent on pressure. Direct brine releases are dependent on pressure and brine saturation both. So because that new volume in the north end may impact pressure and brine saturation, these two release mechanisms specifically, we did an impact assessment to determine what that additional volume would do to spallings and DBRs. So I'll say a little bit about the necessary conditions for these. As I said, spallings release volumes are directly dependent on pressure. You have to have pressure bigger than 10 megapascals to get a spallings release due to the tensile failure of the repository material. Direct brine releases depend on pressure and brine saturation. You have to have pressure that's at least 8 megapascals. That's what's assumed to be the hydrostatic pressure of the drilling fluid in WIP PA. And the brine saturation has to at least exceed the residual brine saturation of the waste, and that's a sample parameter that we use. So if those two conditions are met for DBR then you have a direct brine release. If you have pressure bigger than 10 megapascal, you can have a spallings release. So I'm not going to put up a lot of plots about what that impact assessment saw. I'll just summarize it here. And the proposed additional excavation for salt resulted in, as I sort of hinted at starting out, lower average pressure in repository waste regions, slightly higher brine saturation, an overall reduction in spallings releases, really no change to DBRs. I mean, the pressure and brine saturation changes were small enough they didn't do a whole lot. But no noticeable changes to total normalized releases. This additional excavation was shown to have a negligible impact on repository performance. So we included that in the 2014 compliance recertification application PA. So now we'll switch gears a bit to talk about parameter updates that we've done, that were done and included also. And we'll start with what I call just standard updates. These get done every time we do a new recertification to submit to the EPA. The drilling rate, if you remember that box of WIP and all the little boreholes around it, the rate those boreholes are in place is tracked, so we update this drilling rate parameter every time we do a recertification PA. Once those boreholes are used to extract resources and then abandoned, they're plugged in different ways. The ways that they're plugged is also tracked, and that gives us a probability on the way those boreholes are plugged. That's also used in PA for WIP. The new inventory is updated, and then radionuclide solubilities and their uncertainty. So I'll say a little bit about the inventory. It has a slightly higher activity in the 2014 PA than it did back in 2009. So here's the 2014 activities, this red curve, and the 2009 one is here. The difference is primarily due to increased plutonium-239 in the updated inventory. And you may notice this date here. So this is a 2014 recertification. We're using data from 2011. That seems like a big gap. As I mentioned, this whole package has to be submitted to the EPA in March of 2014. We do the performance assessment and the analysis primarily in 2013. We get the performance update, or the inventory update rather, at the end of 2011. That has to be analyzed and the meat pulled out of it. That takes a good portion of 2012. So there's a 2 or 3 year lead cycle between the inventory and the PA, just because of the process involved. And there were a number of parameter and implementation changes that we made in the 2014 recertification PA. We'll talk about those now. In our motivation for doing these, we heard a lot of talk at this technical exchange, how there's so much conservatism built into performance assessments, and you stack that and stack that and stack that. You really know what you're getting at the end. Maybe you don't even have anything that's conservative anymore, because maybe they're interacting in ways that you don't really understand. So that was our motivation for refining these parameters, was just to try and remove some of that over-conservatism in our PA models. So the waste shear strength, steel corrosion rate, the probability of encountering pressurized brine during a drilling intrusion in the future. And we made a more explicit dependence of radionuclide concentration on the brine volume in the facility, expanded the water balance that we use in the chemistry model, and there were colloid enhancement parameters. These first bullets, except for the last one, this first set, were things that we undertook and did at Sandia and Carlsbad. So I'll talk mostly about those. These are our partners at Los Alamos did. I wasn't involved in those, so I'm not going to say a whole lot about them. About that one specifically. So the waste shear strength is really, when you look at the sensitivity analysis, the dominant parameter as far as releases are concerned, the most important. It's the ability of the waste to resist erosion. It's one of the most important parameters in WIT PA. As we saw in those plots I put up earlier, cuttings and cavings are the dominant release mechanisms. Cavings volumes are a function of waste shear strength. So if we can get our hands better on the shear strength of the waste, we can have a better representation of the cavings volumes that come out during a drilling intrusion. And here's our experimental facility that we used, a vertical flume experiment. We use that to determine a refinement to the waste shear strength parameter. So do you have a question? Or? Okay, you had like you were thinking about something. Surrogate waste samples were used to determine a lower value of the shear strength uncertainty range. And the vertical orientation of this experimental facility is important. There's been data developed in the past where shear strength of surrogate WIP waste was developed for a horizontal moving flow field, but that's not how the flow is going to be if somebody sinks a borehole down into the waste. That brine's coming up, not across. So this was important to the regulator that this data be generated for an experiment that's a more typical representation of what a borehole intrusion would be.
Yes, I do have a question. You talk about waste shear strength. Does that include the containers?
Mm-hmm.
Or is it basically the shear strength of the containers or the shear strength of what's in the container?
It's sort of all mixed together.
I think it's all, there's all kinds of stuff.
Mm-hmm. Yeah, there's plastic and all kinds of stuff.
Yeah. You're wondering how to figure it out. Yeah. What are you calling waste that you're estimating the shear strength of?
What do I call it?
Which wastes are you trying to figure out the shear strength of, or
It's
the containers, or some composite wall?
It's a composite. And we look. So this is the only slide I have about that. So we looked at different percent degradations of representative waste materials, put those in this experimental facility, and saw how the shear strength was different. So if that waste was 75% degraded, you get something different than if it's 50% degraded. There's a bunch of documentation for this if you're interested in seeing it. It's more than I can cover in a little bit of time. Iron corrosion. Iron corrosion is important in WIP PA because when waste gets wet, the iron gets wet, you have gas generated. That generated gas impacts repository pressures, and that changes all of our release mechanisms. So steel coupon samples were used at the Sandia facility in Carlsbad to experimentally determine updated iron corrosion rates. They were done over a number of years. We used that new data to generate a new uncertainty distribution for iron corrosion that gets fed into the gas generation model. The result was that there was lower repository pressures on average with this new updated iron corrosion rate. And we keep seeing this kind of a picture. Pressurized brine encounters. I've already talked about somewhat. WIP PA includes intrusion scenarios that model borehole drilling through the repository and into an underlying region of pressurized brine. It's hard to see. So some of these dots are red and some are black. So these are all the boreholes that have been sunk around WIP that have been tracked. And part of what they track is whether they encounter pressurized brine or not as they're putting that borehole in. So in this little elliptical region here, there are a lot more red dots than anywhere else. So we use that region to update the probability of hitting the pressurized brine region during a drilling intrusion.
So are all of those vertical, are all of the oil production or gas production going to be all vertical, or are there some of them out horizontal?
Vertical as far as, so you mean going in and then trying to go out? Yeah.
I mean, ton of horizontal drilling going on to enhance oil and gas production.
Right, right. Yeah, so this doesn't.
I mean, in their production, wherever their production zones are, they anywhere close to the unit where we're putting our research?
Mm-hmm.
And are you considering a scenario with that horizontal, they would put a horizontal pole?
Right, we aren't yet. Because they're not allowed to go underneath WIP.
You're sure they're not?
I think. Say again?
Do you know if they were conventional with oil and gas or not?
I don't know. Yes, this is just the drill logger just writes down where they hit brine or not. So we use that percentage of brine encounters, at least for this parameter, to update the probability of encountering a pressurized brine region during a drilling intrusion.
So is the uncertainty whether there is brine below WIP, or is it the uncertainty of
Encountering it.
So you know it's there?
Yep, we know it's, so they've hit it,
Okay.
they've hit brine
Yep.
before. There's a, you can't see, there's a little red dot right there
Yep.
in the middle. Yep.
I just can't see the scale. Can you tell me what a mile is?
Maybe.
Square is 5 by 5, right?
Each of those big squares?
Yeah.
is side by side?
Yeah.
The black
The
square.
land was drone.
The little-
Yeah, this is
little
five,
box
so this
squares
is-
are side by side?
This is 0 to 10 miles there. So this is, it's 5 by 5 this way.
What, the green?
Mhm.
The green is 5 miles across?
No, just the whip side, this little box.
That's 5 miles.
Uh-huh. So this one, I'm not a chemist, so I'm going to explain this in sort of big general terms, because that's the way I understand it myself. Radionuclide concentrations in brine are dependent on the repository brine volume. That seems like a no-brainer thing to say. Of course, if you have a larger brine volume, that concentration of what's in it's going to go down. But that's not been the way it's been modeled in the past, because there are materials in the waste inventory that impact the solubilities of radionuclides. For example, organic ligand material can impact how soluble the radionuclides are. And the way it's been done in the past is to take a fixed brine volume, dissolve all that organic ligand material in it, use that concentration to determine what the radionuclide solubilities are. And what we did for this one was to take that organic ligand concentration to map it out to a set of increasing brine volumes. So we have a more realistic representation of how solubilities will change depending on the volume of brine in the repository. So you see that here. We'll use that smallest brine volume at 17,400 cubic meters, dissolve all the organic lignin material in that, figure out what the actinide solubilities are. Here's what the total concentration curves look like. We take 5 times that minimum volume, use that for the solubilities. We see a drop in concentration, as you would expect. You have more brine, things aren't as concentrated. So this is a more realistic representation of radionuclide concentrations in brine as opposed to what was used before. The water budget refinement. There's magnesium oxide placed in the repository. One thing it does is sequesters CO2. It's put there for a variety of reasons. So what we wanted to do, and we thought was important for this CRA, was to refine the repository water balance to include a more complete set of gas and brine producing and consuming reactions for the existing conceptual model. So here are the additional reactions that we included. MgO hydration consumes water and produces brucite. The carbonation of brucite forms hydromagnesite. Hydromagnesite dehydrates to form magnesite. And also iron hydroxide sulfidation produces water. So what this tends to do is if brine gets put in the repository, that brine gets sequestered for a period of time. As these reactions occur, then gets released later. Yeah, there's a lot of chemistry reactions that describe these, but I didn't think it'd be good to get into those details in this small of a presentation. So now the approach and results. So we get to the meat of what we found as far as the compliance curves go for this recertification application, PA. This was the new approach we took to do the analysis and to present the results to the regulator. Because there are so many changes, we didn't want to just throw everything in there, get a compliance curve, and give it to them, because they wouldn't be able to tell what change is driving the curve, which way. If we have lower releases, what's driving that? So it was important for us and to them to be able to sort of walk through each change and show how the compliance curves are changing, so they can pick out this parameter change has a big impact. This one doesn't really do anything, but is there to keep the physics more realistic, things like that. So we split this performance assessment into 4 cases. The 4 cases are denoted by these hyphens. So hyphen BL stands for baseline. So you have the new panel closure design in there, the additional excavation, the updated inventory with the solubilities, but those solubilities are only based on that single brine volume instead of 5, as I was just talking about. Updated drilling parameters and the revised colloid factors. Once we have the compliance curves for that case, we step over here and include the revision to the tau fail, the waste shear strength parameter, and the probability of encountering pressurized brine under the facility. So this hyphen TP, that stands for tau fail, that's the name of that parameter, in PA for waste shear strength, and P brine. So it includes all of these changes plus these 2. You step to the right here, we have hyphen BV. So that includes all these changes plus the more explicit dependence of radionuclide concentration on brine volume. So that's what the BV stands for here, is brine volume. So the last case includes all of these things plus the steel corrosion update and the water budget refinement. So we have curves for each of these that we can look at as we're doing the analysis to see what each parameter change does, and we can show to the regulator, sort of walk them through, this is what's changing what, and these are the things that don't matter, this is the change that really matters. So for the baseline case, this light blue curve here is our current regulatory baseline from 2009. And this maroon curve is the baseline case from CRA 14. And there's a slight increase when you look at these 2 compared, primarily due to the increased waste activity. There's been more drilling there. The oil industry is really booming in that part of the country right now. And the revised solubility for thorium in the +4. So those changes together bump that compliance curve a little bit closer to our release limits. When we include the new waste shear strength and the probability of encountering pressurized brine under the repository, we get this sort of a drop from the previous case. So here's our baseline case. We put in the new waste shear strength and that new probability for encountering brine, and our compliance curve moves to the left. It gives us a little more slack between what we have and the release limit. So why is it doing that? That's shown on this curve. As I said, cavings releases are really dominated by the waste shear strength. They really determine the cavings releases. And when we update that waste shear strength parameter, we go from the dashed red line to the solid red line for the compliance curve for cuttings and cavings. So that gets pushed away a good bit from the release limits. And when we update the probability of hitting brine, that also drops our direct brine release compliance curve a bit. So you have a drop from the blue dashed line to the blue solid line. So those two things together, they dominate really total releases. So up here, this curve is dominated by cuttings and cavings. Down here, it's dominated by direct brine releases. So when you put that change together, you shift this whole curve to the left. When we look at the more explicit dependence of radionuclide concentration on brine volume, and include that in the next case, this is BV for brine volume. You see another little drop here in releases. You get a reduction in direct brine releases from the previous case to this hyphen BV case. And that's just because you have a given volume of brine coming up during that intrusion, but there's less material dissolved in it as that brine volume is increased. So your direct brine releases decrease on average. So the hyphen 0 result, so it includes everything I've talked to up to now, plus the iron corrosion update and the expanded water balance. And all you see in the total release curves, that's these two black, so the black dash, and then from the previous case, and the black solid is with all the changes included. You see this little wiggle here. There's not a whole lot of impact from updating the iron corrosion or the water budget. And that wiggle is direct brine releases are changed a little bit. Falling releases depend directly on pressure. So if you change iron corrosion and change gas production, it goes down. Falling releases.
Took a new approach, implement them sequentially, so we could walk ourselves through it, walk the regulator through it, just so we could be more comfortable with what we're talking about to them, they can be more comfortable talking about their voice to stakeholders. So at the end of the day, we have to take this to the public and they get their statements. We did the total normalized release of the main this area 24 century or less than those found in the current baseline, but